Hi folks, sorry again that I can't be with you today. We're going to try this lesson interactively. I hope it works. If not, I've left some backup work as well with your cover tissues. But it should be that you can all listen to this through your headphones, and as long as the bandwidth in the classroom holds out, then you should be absolutely fine. Okay, we've got two starter questions to start us off. One on straight line, all about a point coordinate being missing, but you're given a little bit extra information that should allow you to find the value of a. And then for number two, we've got a trig function there to solve. I have had a few people come into support study and the penny drop with trig functions this week, so good job to you guys. If you know who you are, shout out to you. I want everybody practicing this because this is going to be a major thing in our November assessment. Okay, I'm going to go through the answers in just a couple of seconds, so if you need, well, you definitely will need, pause the video here and then restart when you're ready to have a look at the solutions. Alright, okay. So the first one here, we're given that the points are 4, 5 and 2a. We know that AB is perpendicular to the line with equation 4y plus 3x equals 8. Alright, so the first thing I'm going to do is I'm going to focus on that straight line equation in the second sentence there. If I rearrange that, I can get to the point where we've got y equals mx plus c. Okay, so the first thing I'm going to do is I'm going to take 3x from both sides. So 4y is equal to negative 3x plus 8. Oops. And then dividing by 4 on both sides, I get that y is equal to negative 3/4 x plus 2. Okay, so I know that whatever the gradient between points A and points B are, has to be perpendicular to this. Alright, in other words, perpendicular to negative 3/4 is going to be positive 4 over 3. All I've done is I've flipped the fraction and changed the sign. Okay, so because it started off negative, I flipped the fraction and made it a positive fraction. Okay, so working through this, what I'm going to do now is I'm going to try and find the gradient from A to B as it is with my mystery point in there. Okay, so y2 minus y1 over x2 minus x1. I'm going to substitute in my two coordinates that I have in my question. I've got 5 take away a, and I've also got negative 4 take away 2. Alright, so I know that my gradient has to be 4 over 3, so I might just put that in as well. 4 over 3 is equal to all this. 4 over 3 is equal to 5 minus a over negative 6. Alright, what I'm going to do is I'm going to try and make an equivalent to the fraction on the left hand side over here, but with negative 6 on the bottom. So I'm going to multiply this 3 by negative 2, and that will make negative 6. Right, but whatever I do on the top of a fraction, I have to do on the bottom of the fraction as well. Okay, that'll give me that negative 8 over negative 6 is equal to 5 take away a, oops, over negative 6. That means that 5 minus a is equal to negative 8. Alright, all I've done is I've got rid of the negative 6's on the bottom of each of those fractions. Then if I rearrange this, I'll plus 8 on both sides. That'll give me 13 minus a is equal to 0, and then that means that our a value here is 13. Okay, and that's us found the value of a there. Using, first of all, the equation given to us in the question, we've rearranged that into the form y equals mx plus c. We've figured out what the gradient should be, and then we've found the gradient including our variable and rearranged it to solve to get a equals 13. Alright, the second question is a trig function, a trig equation that we have to solve. First thing I'm going to do is I'm going to rearrange my limits. So instead of 0 is less than or equal to x, which is less than or equal to 180, I'm going to say 0 is less than or equal to 3x, which is less than or equal to 540. I'm going to be doing a spin and a half around the cast diagram because 540 ends us just before the trig function, the tan quadrant, the second time you spin around the cast diagram. Alright, the next thing I'm going to do is I'm going to rearrange this equation here so that we've just got tan x, or tan 3x as it is this time. So tan 3x plus 5 equals 3. Right, I'm going to take 5 from both sides. That will give me that negative 4 tan 3x is equal to negative 2. Then I'm going to divide both sides of the equation by negative 4. Right, that will give me that tan 3x is equal to positive 1/2. I've got a negative number divided by another negative number there, so the negatives will cancel out. Tan 3x is equal to 1/2. So 3x is going to be equal to tan to the minus 1/2. Okay, just grab a calculator. Tan to the minus 1/1/2 is 26.565. I'll call that to 2 decimal places. 26.57. Okay, that's one of our answers for tan 3x. Another one would be the tan function as we go around the cast diagram, so it's going to be 180 plus 26.57, or 206.57. Oops, 206.57. Okay, and we'll get a third answer from the all quadrant the second time we go around the cast diagram, so that's going to be 360 on from my original answer, which is 386.57. Alright, to get my final answer, x is just going to be all those numbers divided by 3. So 26.57 divided by 3 is going to be 8.86. 206.57 divided by 3 is 68.86. final answer, 386.57 divided by 3 is equal to 128.86. Okay, if you got those three solutions, you've done very well. Excellent stuff. Right, today we're going to take another wee look into differentiation. We're going to find some derivatives. Remember that our function for finding a derivative, if we've got a function f of x, then the derivative of f of x is written as, after we differentiate, f dashed of x. Right, as you progress further through mathematics, you find that you can do several differentiations of each function. So you could have f double dashed of x if you differentiate twice, or f triple dashed of x if you differentiate 3 times as well. But for now, in higher, we're focusing on just one differentiation at the moment. Okay. Okay, so as I was saying, f dashed of x goes to f of x goes to f dashed of x as you differentiate. Okay, the other thing that happens is that we bring the power down as a multiplier, so this n that was here is now in front of our x term. Alright, and what we do is we take one unit away from the x power. Okay, f dashed of x is referred to as the derived function, or you could call it the derivative of f of x as well. Okay, but what we need to know is that our notation is f of x first of all, and then f dashed of x after we've done some differentiation. So what I first of all want to do with differentiation is just make sure that we're confident in taking something, some kind of function of x, and writing it in a form that we can differentiate. So all of these fractions here on the board right now cannot be differentiated until they're put into a non-fractional form. Okay, because we've got our x terms on the bottom of the fraction, that will cause difficulties unless we change the form here. Okay, so what I'm going to ask you to do first of all is just rewrite these fractions, but with x not on the bottom of the fraction. Okay, I want this in an index form that you can differentiate. Okay, pause the video now, complete these 5, and I'll be right back with the answers in just a couple seconds. Okay, so for those first 5 answers, an x on the bottom of a fraction is going to be x to the power of -1. If there's a higher power, like x to the 5 on the bottom of the fraction, then it pulls up and it becomes x to the -5. For that middle one, if you've got a multiplier on top, it just stays as your multiplier, and the x to the power of -4 comes up. Same with a negative power, don't get confused by that either, that still stays as a multiplier because it's on the top of the fraction to begin with. And if you have a number on the top of the fraction and on the bottom of the fraction, those stay the same as well. Okay, we've got 6 on the top of our fraction, 7 on the bottom, and x just pulls up to the side of the fraction and becomes to the power of -6. Okay, the next 5 indices that I'm looking for, currently they're all in surd form. I'd like you to pull them out of surd form and give me again a proper power of x that we can use differentiation on. Again, I'll be back in just a few seconds with the answers, so pause here until you're finished with these 5 questions. Okay, so for those 5 answers, we've got x in a square root bracket. That square root bracket, remember, is hiding something that we don't put in as mathematicians, but that's the second root of x. So it's just 1 over 2, because your power number is 1 and your square root number is 2. So 1 on the top, 2 on the bottom. With a multiplier in front, that multiplier just stays the same in front. So it's 3x to the power of a half. For this one here, again, that missing number there is going to be a 2 because we don't write that on a square root sign. So we've got 5 over 2 as our power. This one here, both of our numbers are in, so 3 is the power number, it goes on top. 4 is the square root number, that's the 4th root of x cubed. So 4 goes on the bottom of our fraction. And then finally, I've just thrown absolutely everything at you here. 5 is our multiplier that stays in front. 10 is the top of the fraction, and 3 is the bottom of the fraction. So you get 5x to the power of 10 over 3. Okay, for our final 5 questions that I'm sure you've clocked at the bottom of the screen already, I have combined both x's on the bottom of fractions and surds to make one last challenge. Okay, again, just write these functions as powers of x's that we can differentiate. Make sure you pause the video here, otherwise you're going to get the answers spoiled for you just now. Okay, so for those last 5 examples, we've got a multiplier of 4 on the top of the fraction, so 4 stays out front, and then I'm pulling up x to the power of a half, so it becomes x to the power of negative a half. 5 over root 3 of x, or the third root of x, or the cubed root of x, is going to be 5x to the power of negative a third. X cubed over the square root of x, what we need to do is we need to take away the powers here. So we've got x to the power of 3, take away x to the power of a half. Alright, 3 is just the same as 6 halves minus 1 half. So that gives us x to the power of 5 halves. Okay, remember from National 5, your laws of indices are that if you've got the same base to 2 different powers and you're dividing them, all you do is take away the bottom power from the top power. Okay, same with this one. We're taking away 7 over 2 from 1, and that will give you negative 5 over 2. And our final one here, I've written out the fraction calculation that you have to do, but we're doing x to the power of 5 over 2, take away x to the power of 3 over 4, and that leaves us with x to the power of 7 over 4. All right, again, if you're not sure about how I did that, what I would have done in this calculation is double both of the numbers on the left-hand side. That would give me 10 over 4, and then they're both in quarters, so I would just take them away after that. Okay. I'm going to erase just this bottom part here. And then I'm going to issue you with your next challenge, which is, okay, we've now put all these functions in differentiable form, if that's even a word, differentiable. I'd like you to differentiate each of these functions, please. Okay, I'll come back and provide the answers to these differentiated functions in just a couple of minutes. Okay, make sure that you pause the video here so you don't get spoiled for any of the answers. Okay, so coming in with the answers for these functions. I'm going to do them in green and purple just to contrast with the colors that we've already got in here. So your differentiated form of x to the minus 1, we're going to get f dashed of x being equal to negative x to the negative 2. If you put that back into fraction form, then well done you. But that's the minimum answer I'm looking for right there. For the next one, I might do above and below as well. For number 2, f dashed of x is equal to negative 5x to the power of negative 6. Be careful with the direction that you go when you're taking away 1 from a negative number. We're going to go further into the negatives, taking us down to negative 6. For this one, number 3, f dashed of x is equal to negative 12 x to the power of negative 5. Number 4, f dashed of x is positive 16 x to the negative 9. Number 5 is going to be horrible, f dashed of x equals negative 36 over 7 x to the power of negative 7. Okay, for these next ones I'm going to have to be, again, a little bit more delicate. So this is going to be half x to the negative a half. Again, if you've managed to put this back into fractional form, an even surd form, then kudos to you. This is the minimum answer I'm looking for. For the next one, 3 times a half is going to be 3 halves. So 3 over 2 x to the negative a half. For number 3, the 5 over 2 comes down. So 5 halves come down, and then I'm taking 2 halves away from my power because 2 halves make a whole. So my final power is going to be 3 over 2. Okay, the next one, again, 3/4 comes down. I'm going to be taking 4/4 away because that's the same as 1. So I've got 3/4 here. Oops. Getting a little bit messy. And my power is going to be 1/4 into the negatives. So negative 1/4. I'm going to take this away, I think. So for this last one, f dashed of x, 10 over 3 times 5 is going to be 50 over 3. Then because my power is in thirds, I'm taking away 1 in thirds, which is 3/3 away. So I'm left with 7/3 as my new power. Okay, one more line. Finishing this off. F dashed of x, for this one we're doing negative a half times 4, which is negative 2. And then taking 1 away from the power, I'm taking away 2 halves from negative a half already, so it's going to be negative 3 halves. F dashed of x in this case is going to be negative 1/3 times 5, so it's negative 5 over 3. X, and I'm taking away 3/3 from already negative 1/3, so negative 4/3. For number 3 here in this row, 5 over 2 comes down. And we've still got x to the power of 3 over 2 left. One's actually one of the nicer ones in this row. For number 4, minus 5 over 2 comes down as our new multiplier. We're taking 2 halves away from the already negative 5 halves. So that gives us negative 7 over 2 is our power. And then the final one, f dashed of x is equal to the 7 over 4 comes down. Because we're working in quarters, I'm going to take 4 quarters away from my power number, and that'll leave me with 3 quarters as the power that's left. Okay, again, I think that's a reasonably nice one in comparison to the first, second, and fourth of that row. Wow, if you can discern all that, very well done. If you manage to get all those right, even better. Okay, so we're moving on to another topic in differentiation. But first I want to talk about a couple of different types of notation. So there are 2 very influential mathematicians who impacted the work in terms of notation around differentiation. Okay, right here we have Wolfram Leibniz on the left-hand side. I like to call him Wolfie. Wolfram Leibniz was the person that we are going to look at his notation in just a second. There's also Joseph, that says Joseph Lagrange. He is the person who is to blame for your current notation, which is your f dashed of x notation. Okay, he was primarily an engineer. He worked mostly with sets and functions that were written in function notation, so he developed a function notation way of writing down differentiation problems. Leibniz, on the other hand, he was mainly into geometry. He was used to his straight lines. He liked working with y's and x's. So his version of a differentiation, when you have y equals something, let's just say x, then when you differentiate, you get dy over dx, which is pronounced dy by dx. Right? And this stands for the differentiation of equation y with regards to differentiating x. Okay? All right, if we were to differentiate the function that's on the left-hand side here, x differentiates down to 1. So dy by dx would be 1 there. Okay? So Leibniz was primarily into his geometry. That's why his notation is mostly to do with y's and x's. Joseph Lagrange over here, he was into functions. That's why his notation works with function notation. All right, we're going to do a few geometry problems now. So we're going to be using Wolfram Leibniz's notation. Okay, so Wolfie's the guy that's to blame for this next part of the lesson. All right, so here's some Leibniz notation. Just a reminder that what I was just saying, for any function y equals f of x, the derivative can be written dy by dx. Okay, it means differentiating y with respect to x. Okay, so differentiating y, but we're looking at all the x functions and differentiating those things. Okay, so we're going to look at finding the tangent of a function at a specific point. Okay, so just a reminder, a tangent is a straight line that only passes through one point on a function or on a circle or on a curve. Okay, to find the equation of a tangent at any point on a curve, we need the coordinate of the point that we're going to be going through and the gradient at that point. And we can use differentiation and our knowledge of functions to find both of those things. Okay, so I would copy down this example into your notes jotter. I'm going to go through it in just a second, but make sure that's in your notes jotter first. So pause the video and I'll go through this in just 1 second. Okay, so there's 2 things that we need to find. We need to find the coordinate that we're using, and that is quite easy. That's National 5 Maths. We can do that with no problems. Then we need to find the gradient, which involves a little bit of differentiation, but again, nothing new to you because we've already done evaluating derivatives at a particular point. Okay, to start this off, right, find the coordinate. I know that y is equal to x squared times by 3 minus 2x. That's from my question just above there. All right, I also know that we're looking for the tangent to the curve where x is equal to 2. So what I'm going to do is I'm going to rewrite this function here, but instead of putting in x squared, I'll put in 2 squared because x is equal to 2. All right, and instead of 2x, I'm going to put minus 2 times 2. All right, if you work this through, 2 squared is equal to 4. We're multiplying 4 by 3, take away 4. Right, so that's 4 times negative 1, which is just negative 4. All right, so the important coordinate that my tangent is going to be going through is going to be x is 2, that comes from the question, and y is negative 4, that comes from substituting 2 into the function. Okay, second thing we're going to do is we are going to find the gradient of this straight line here that we're going to be using. So what we're going to do is, first of all, we're going to put y into a differentiable form. I'm going to expand these brackets just to be able to differentiate. So instead of y being equal to x squared bracket 3 minus 2x, right, I'm going to just expand that bracket and I'll say x squared times 3 is 3x squared, and x squared times minus 2x is minus 2x cubed. Okay, what I'm then going to do is I'm going to differentiate this. So using Leibniz notation, right, I'm going to differentiate and I'm going to get dy by dx. Right, the differentiation of y with regards to x. Oh, my mouse is starting to not respond to me. Okay, so if I differentiate 3x squared, the 2, the power that is 2, comes down and multiplies that 3, so I'm going to get 6x to the power of 1. I don't need to write to the power of 1 because the power of 1 is just assumed when there's no power there. And then same for the second bit, I'm going to bring the 3 down and multiply it by the 2, so that'll give me 6x, and then the 3, which is the power, gets reduced by 1 to 6x squared. All right, to find the gradient, again, I know what my point is. My x point has 2 as its value, so I'm going to substitute this in. I'm going to find dy by dx at the value x equals 2. So I'm going to write at x equals 2, dy by dx equals 6 times 2. Take away 6 times 2 squared. That's going to be 12 minus 6 times 4, which is 24. So my gradient at this point is negative 12. All right, just a small reminder that the two things that we need to find the equation of a tangent is the coordinate that it goes through. We've got that in blue at the top of the screen. We need the gradient of the line, which we've got at the bottom of the screen in red. Okay, so now I just need to piece that information together. I'm going to use the old nat5 formula. Y minus b equals m bracket x minus a. I'm going to substitute in my formula, which is y plus 4, that negative 4 and the negative in the formula will cancel out. It's equal to negative 12 bracket x minus 2. Right, and then I'm going to go about rearranging this in order to find it in the form y equals mx plus c. So y plus 4 is equal to negative 12x plus 24. And then taking away 4 from both sides, y is equal to negative 12x plus on 20. Okay, and that's my final answer there. My formula for my straight line in the... Okay, so I've got my final form there, which is in the form y equals mx plus c. Right, to finish off today, this is your last activity. What I'd like you to do is I'd like you to find the equation to tangent of each of these curves at the given points or at the x values that are stated, okay? For the first two, because you've got the coordinates already, you don't have to go ahead and do that blue step, the first step where I substituted the x value in to the original function, okay? You've already got your coordinate there. For D, E, G, H, and the 3 at the bottom as well, you will need to put your x value into the function to begin with to find that coordinate. Then you can go ahead and differentiate afterwards. All right, be very careful with your powers. We went through all the different types of indices that you could come up against, apart from the question in G, which is one where you'll have to separate this fraction here into two separate fractions and then sort them out separately. So we've got x over x, which shouldn't be too difficult to sort out, and take away 1 over x, which will be something that you have to differentiate. Okay, I'm going to leave you with that activity. We'll maybe go through this next time I see you as well. But for now, thanks very much for listening this far, and I'll see you all next week. Have a lovely weekend if I don't see you.